So, today we will discuss about some parameters which are useful for crystal structure. So, this we have seen that seven crystal system where this the lattice points are considered at the corner of the unit cell or this pattern unit. So, but Brebis considered the off center or off corner some lattice points which satisfy the condition that the surrounding of those additional off corner points satisfy this the surrounding will be same as the surrounding of the corner points. Okay. So, this so considering these off corner points, so this 7 crystal system basically it is 14 Brebis lattice. So, so let us consider the cubic system, cubic crystal. So, for cubic crystal system have 3 Brebis lattice. So, one is simple cubic, crystal. So, this this simple cubic, this corner has lattice point, each corner has lattice point. So, 8 corners, 8 lattice point. So, another Brebis lattice is body centered cubic. Body centered cubic. So, in this case so 8 corners is are having these 8 lattice points. In addition, along the body diagonal, there is a one more lattice point. So, along the body diagonal, if you take this and I think if I just add this one, so here there is additional lattice point. So, this the body centered cubic crystal, and then face centered, another Brebis lattice face centered. Face centered. So, in this case, so if you so 8 corner will have 8 lattice point as in case of simple cubic. Okay. And at the in each face, so there are 6 faces. So, in each face, at the center of each face there are additional lattice points. So, it will be here, it will be here. Okay. And 2 more on this face, and this other one is this face. So, 6 additional 1, 2, 3, 4, 5, 6 additional up corner points. So, it forms the it's face centered cubic crystal. Okay. So, this for other crystal system also there is additional Brebis lattice. So, like orthorhombic, it has 4 Brebis lattice, and these 3 simple body centered, face centered, orthorhombic, and in additional base centered. Okay. So, that we have discussed. So, today basically what we want to find out that some parameters, so which are useful to study the crystal. So, this if we want to calculate some parameters, say one is number of lattice point, per unit cell. So, how to calculate that we want to see. Then what is the volume of the unit cell? How to calculate that one? Volume of the unit cell. Then also one can calculate the number density of unit cell, means how many number of how many number of lattice point per unit volume. So, basically if you calculate these two, if I write this will be say n and volume of unit cell is V. So, lattice point density in the unit cell or in the crystal, lattice point density that will be, say it is rho n, lattice point density say rho n, it will be n by V, right. So, if we want to know the mass density in terms of mass, if we want to know the density of the crystal, so then if say it is rho m, so how we can find out? So, we know this 1 gram mole of any material contains Avogadro number of atoms or molecules. So, here say atoms are at the lattice point. So, mass of Avogadro number of atoms. So, mass of one atom will be this molecular weight divided by Avogadro number. So, this for 1. So, if n number of per unit cell n number of lattice point or atoms are there, so into n. So, this is the total mass of the atoms in a unit cell. So, volume of the unit cell is V. So, divided by V. So, that will be the mass density. Okay. So, then other parameters also there are like packing fraction, cracking fraction of a crystal. This basically unit cell have volume. Now, what are the ratio or proportion of the volume occupied by the atoms? So, volume of the say V, volume of the atoms in a unit cell divided by the volume of the unit cell. So, this ratio will is called basically packing fraction. So, how much packed with the atoms in that crystal. So, from that this data one can understand. This other parameter is there, this coordination number. Coordination number, that is basically for any lattice point how many nearest neighbors are there which are equidistant from that lattice point. So, that is called the coordination number. Okay. So, that also we will calculate. So, let us calculate first this number of lattice point per unit cell. So, this is the in case of simple cubic. So, in this unit cell 8 corners are there. So, 8 lattice points are there, but now this, so this it is not that 8 lattice point per unit cell, because this each corner, because this is a one unit cell in a crystal. So, crystal basically is formed or lattice is formed just translating this unit cell in all directions. Okay. So, each corner will attach with how many unit cell that we have to find out. So, you can see that, so this side there will be one, okay. So, on top of it 2 more. So, these 4 will have these corners, okay. So, so these are on this plane. If you think that's one is here and 2 more are on top, then this side 4 more unit cell will be there. So, basically each corner will attached with the 8 unit cell. So, this it will share with 8 unit cell. So, for each unit cell, this it will contribute 1/8 of this, 1/8 of each lattice point. So, we have 8 lattice point. So, basically effectively it will be 1 lattice point per unit cell, okay. So, similarly for other cases we can calculate. So, let us, I think it will be easy to understand if we see some model. So, this so we have model for simple cubic crystal. So, this this is a simple cubic crystal, okay. So, this 8 corners, 8 lattice points, 8 corners, 8 lattice point, right, 8 lattice point. So, now if we see here, so here just think this one, each one is 1 unit cell, each one is 1 unit cell, right. This 1, 2, 3, 4, then below 4 are there. So, total 8 unit cell. Now, if you consider just one corner, just if you consider this corner, right. So, this corner, is attached with this unit cell, and this top 4 as well as this bottom 4, okay. So, similarly if you extend this, so you will find that each corner point will attach with 8 unit cell as it is, okay. So, it is obvious that it is it will have 1/8 contribution to each unit cell, okay. So, thus that is what I have written, 1/8 into 8 corners. So, it is effectively 1 unit cell per unit volume, okay. So, this it also expressed nicely here. If you see these are simple cubic. So, 8 corners are there, see, just in each corner, so this is the lattice point, this portion is, that is 1/8. So, this 1/8, this side 1/8. So, this one, so it will be half, and top this 4 parts. So, that will give half. So, this total will be for 8 corners 1/8 into 8 corner, 8 lattice points. So, that effectively will give 1, okay. So, similarly other one, if we consider the body centered cubic. So, this is the body centered cubic, right, as I have drawn, and in model you can see. So, this is the cubic unit cell, 8 corners are there, 8 lattice points. So, one more at the center of the body. So, So, then easily you can calculate how many lattice points per unit cell. So, obviously 8 corners will give you one contribution, effectively one lattice point per unit cell, and one more there in body. So, it is not sharing with any other unit cell. So, total will be 2. So, for body centered, so it will be 1/8. So, I can write 1/8 into 8. So, there is a from the corner plus this one in body. So, it is effectively 2. So, 2 lattice point per unit cell. Similarly, for face centered cubic, how many will be there? So, from model we can see. So, I have so this is the face centered cubic. So, you see 8 corners are there. So, 1/8 from each corner. Now, if you see this, each face will basically attached with the 2 unit cell. So, on top of it another unit cell, on top of another unit cell. Okay. So, this face centered that lattice point. So, it will share with the 2 unit cells. So, it will contribute half to each unit cell. Okay. So, that is why here this you can see this half of the lattice point in this unit cell. So, I have 6 faces. So, this from opposite faces. So, these 2 opposite faces, one more. So, other 2 opposite faces. So, one more. Okay. So, total 3 plus from corner 1. So, total we will get 4 unit cell, 4 lattice point per unit cell. So, here basically we are getting 1/8 into 8. So, from corner plus half from each face. So, into 6 face. So, equal to 4. So, in face centered cubic, so we have 4 unit cell, 4 lattice point per unit cell. So, so this n basically for this simple cubic it is 1, n equal to 1, for this n equal to 2, and this for face centered n equal to 4. Okay. So, next let us calculate the volume of the unit cell. Volume of the unit cell. So, let us concentrate for this case for cubic, or basically you can consider tetragonal as well as orthorhombic also, where these crystal axes are mutually perpendicular to each other. So, in this case volume we can write. So, I think I can so volume we can calculate taking the dot and cross product of lattice crystal axis. So, crystal axis, if it is A, B, C, if it is A, that is say B, and that is say C. Okay. So, what will be the volume? Volume we can write in this case. Okay. I will write A cross B dot product with C. So, A cross B is basically the you know the I mentioned probably. So, this tells about the area, it tells about the area, okay. This is the area A cross B. So, this is B axis. So, this parallel to this. So, this is B and this is A. So, this area is AB. AB. So, here if I take, I can write AB sin theta, I can write AB sin theta, but if it is cubic crystal or tetragonal or orthorhombic, so this theta is 90 degree, okay. So, it will be 1. So, it will be for cubic system or this orthorhombic system, it is AB, and if it is cubic, so it will be A square. So, there A equal to B, and direction, this is the plane, this is the plane, and direction will be say unit vector n. So, that will be perpendicular, that will be basically perpendicular on this plane, okay. So, then I can write this, I can write this, okay. So, in this case, if it is cubic or orthogonal system, means this all three axes are mutually perpendicular to each other. So, this n, it is the direction will be c direction. So, this n is basically c direction, unit vector towards this, towards c. So, this cross product, if I take A, B, C and this cos theta, say if I write just one angle. So, this theta is 0 basically, right, because they are in same direction. So, it will be cos 0 is 1, so it will be ABC, okay. So, for cubic crystal it will be A equal to B equal to C, A equal to B equal to C for cubic system. So, it is A cube. So, volume of the unit cell, cubic unit cell is A cube. For tetragonal orthorhombic, it is ABC, okay. I think tetragonal it is A square C, and orthorhombic it is ABC, okay. So, now you can, so this volume is, this volume is same for simple cubic, for body centered cubic, and this face centered cubic, right. So, easily I can calculate density, So, rho n for simple cubic, I think I will write here this for simple cubic, rho n equal to n by v, n is 1, v is A cube, okay. So, that will be the lattice point density for simple cubic, lattice point density for body centered cubic, it will be 2 by A cube, and lattice point for lattice point density for body centered cubic will be, sorry, for face centered cubic will be 4 by A cube, okay. So, if you know the mass of 1 gram mole material, then Avogadro number is known to us. So, for that material just we can get the mass density, okay. So, that way we can calculate these parameters, and these are very important parameter that we will see later on. So, similarly this other two, this packing fraction as well as the coordination number we can calculate. So, for packing fraction, to calculate the packing fraction, we need the radius of the atom. So, here we have considered the lattice point. So, actually it is not representing the real crystal. So, to get the real crystal, so these are just mathematical concept. So, for real crystal basically we have to add. So, with lattice we have to add basis, it is called basis, then we will get real crystal system, right. Okay. So, real crystal system, I think real crystal system. So, this so basis is basically atom or group of atom attached to the each lattice point in same manner. Okay. So, that if it is one atom, it can be just at the position of lattice point. If it is two atom, say sodium chloride, in case of sodium chloride, so each basis will consist one sodium and one chlorine atom. So, that sodium and chlorine, just it is, I am not putting exactly, just one can put this way. So, here one sodium, here one chlorine. So, then we have to put attach this group of atom in same manner. Okay. So, these are called basis. So, lattice plus basis with each lattice point will give the real crystal structure. So, now this in real crystal structure, there these atoms are there or group of atoms are there, then to know the packing fraction, so we have to find out the radius of the atoms, and we have to assume that in at the smaller distance between the lattice points, okay, along that these atoms will touch each other. So, from that assumption, from that concept, one can calculate, find out the radius of the atom, and from there we can get the packing fraction of the unit cell, as well as it will be required for calculating the coordination number of the lattice point. Okay. So, I will stop here. Thank you for your attention.